Hopefully you tried these on your own. I did warn you they'd be a little bit trickier than what you'd seen already. This one says, if I have a sample of 5 grams of calcium hydroxide dissolved in 0.5 liters of water, what volume of 0.2 molar hydrochloric acid must be added to reach the endpoint of the titration? So we know if we're doing a titration, we're going to want to use the equation we've been using, our MAVA equals MBVB. So we're going to start with what we know. We know our number of OHs in our base, I'm going to actually start with the base, equals 2 because we're doing calcium hydroxide. Our molarity of our base is equal to something, but we know molarity should have an M after it. All we've got is this 5 grams here. But remember that molarity is our concentration, and that's in moles per liter. So what we're going to have to do is convert our grams to moles and then use our volume. Well, there's actually an easier way. If you figure out how to do the easier way, do it that way. Let me know. So we know our volume of our base is going to be 0.5 liters. This is frankly more than you usually use on a titration. I was trying to make y'all's math easier. We know our number of H's in our acid is 1 because it says we've got HCl. We know the molarity of our acid is equal to 0.2 molar, and we're trying to find the volume of our acid. So before we do all that, we already said we know stuff about the molarity of our base. We're going to have to actually find the molarity of our base. So we know it's moles per liter for molarity. So we've got, 5 grams. 5 grams of CaOH2. And we're going to have to do the fact that 1 mole equals the molar mass, which we add up from the periodic table. And so we're going to have 40.08 plus 16 times 2 plus 2.02 times 2 to give us a total molar mass of 76.12 grams. Okay? So now we're going to divide our 5 by our 72.12. So we have 0.069 moles, and we said molarity is moles over volume in liters, and our volume was 0.5 liters. So our molarity of our base is going to end up being 0.139 molar. And yes, I usually tell you to round to 2 decimal places, but while you're still doing your math, you want to keep some extra places around. Alright, so now we plug it in our equation. We've got 2 hydroxides times our molarity of 0.139 molar times our volume of 0.5 liters, which is equal to 1H times our 0.2 molar times the volume of our acid, which is what we're looking for. And as usual, we can just do our algebra from here. We're trying to get VA by itself. So we're going to divide by everything that's on the same side. So we're going to divide by 0.2 molar. The 1 doesn't really matter because it's not going to change the value. Divide by 0.2 molar, and a whole bunch of people at this point ask me, but wait, how do I know the units on my volume? If you look, our molarities cancel out. The only unit I have left is liters, so our volume is going to end up in liters at this point. So we have 2 times 0.139 times 0.5 divided by 0.2, and that is going to get us a volume of our acid equal to 0.6, that is not a 6, 0.695 liters, which is frankly an awful lot of acid, but right now we're just doing the math. We're not trying to do it in lab. And our last one. This one's actually a lot simpler compared to what we just did. So even if you didn't try the other one on your own, try this one on your own. So we know we've got a 20 milliliter sample of 1.1 molar nitric acid. We're titrating it with 0.25 molar sodium hydroxide. Then it tells us that if 5 milliliters of sodium hydroxide have been added, how much more sodium hydroxide will have to be added to reach the equivalence point. So we're just going to use the same equation we've been using. So we've got our number of H, molarity of our acid, volume of our acid, molarity of our base, volume of our base, and our number of hydroxides. So our acid in this case is HNO3, which has 1 H. The molarity of our acid is going to be 0.1 molar. The volume of our acid is 20 milliliters. The molarity of our base is 0.2 molar. And it tells us we've got 5 milliliters of sodium hydroxide, but it also wants to know how much more we're going to have to add to get to the equivalence point. So for right now, we don't know the volume of our base. We'll deal with our 5 milliliters later, and our OH is also 1 here. So we go and plug everything in. We know we've got 0.1 molar acid, and we've got 20 milliliters of that. That's equal to our 0.2 molar base times the volume of the base, which is what we're looking for. And again, left the ones out, not going to change our math. So this actually looks a lot prettier. We know we're trying to get VB by itself, so we're going to divide. And we've got molarity and molarity, those cancel. So we plug this into our calculator, 0.1 times 20 divided by 0.2. And so the volume of our base is equal to 10, and all we got left here is milliliters, so it's milliliters. Now, we go back to what our question is actually asking. The question actually asks, if 5 milliliters of the sodium hydroxide have been added, how much more NaOH do we need to reach the equivalence point? So if we've added 5, and we know we're going to have to add 10 total, we just subtract our 5 milliliters that we've added so far. So this is our total needed. This is the amount added so far. We're going to subtract that, and the volume of the base we still need to add is going to be 5 milliliters. Alright, so that's how we do our titration calculations. Try the practice on your own, and then see how it works out in lab.